Okay. So, we are back and we will be discussing small oscillations. So, we have learned little bit about normal modes, normal coordinates, and we have learned the terms like stable equilibrium, unstable equilibrium and metastable equilibrium. Now, out of these three, we will be discussing two, as in we will be discussing primarily stable equilibrium, but also under the approximation of small oscillation, that is very important. We can also deal with systems which are close to in a metastable equilibrium. Okay. So, first of all, what is the term small means? See, small and big, they are all relative. You can call a length, we can call this much small compared to a kilometer, but this is huge when we are talking about a millimeter. So, these are all relative. We need to have some scale in order to define small and large, or small or big, whatever. So, where is the scale in this system? I mean, in these problems which, or in the context of small oscillation, first thing is we have to define what is small. So, let us assume that we have a system which has different degrees of freedom, as in, okay. Let us take a more specific example. We will be dealing with systems which are coupled oscillating systems. Okay. So, let us say we have a system which is it is an infinite spring mass system. We have masses in these points and in between we have springs, and we want to study the oscillatory behavior or the frequencies of oscillations and what not for this system. Now, what is the procedure? What we can do is, if we go by Newtonian mechanics, Newtonian dynamics, we can find out the equations of motion. We can do the same thing using Lagrangian, but that is not the question here. The question here is what is small, right. So, I have taken this specific example because this is a system which is very well known to all of us. Let us say all these spring constants are k. So, we know that the potential energy of a spring which has a spring constant k can be written as half k x square, where x is the compression or extension of that spring, right. So, each of this mass at equilibrium, when the system is in equilibrium, if there is no vibration present in the system, there is no potential energy, right. So, moment you start deviating the system from equilibrium, this deviation is your x, not the individual coordinates. Okay. If the equilibrium coordinate is x 0, what you can do is you can write the equilibrium coordinate as, let us say, x 0, and this coordinate you can write x. So, you have to substitute this with x minus x 0 square, which will be your half k q square. Okay. So, your generalized coordinate or coordinate of interest is the difference or deviation from equilibrium position, right. Now, if it is a system where we have not only one q, but we have, for each of these masses we have q1, q2, q3, q4. For each of these masses I can assign an individual coordinate. So, here the potential energy V is a combination, and we know that energy is additive. We have one particle with energy E1, you add another particle E2 into the system with another particle with energy E2 into the system, the combined energy goes up by E1 plus E2. Same holds for potential energy. So, if this is your V1, then they will have V2, V3, V4. So, total V is a sum over all these Qi squares, right. So, this is a general norm, this is a general form of potential. So, in effect, V is a function of Q1, Q2 up to Qn, n being the number of molecules. Now, n can go very high. We can have 2 mass spring, we can have 3 mass spring, 10, 20, and in the continuum limit we can have almost, in principle we can have Avogadro numbers. Avogadro number is 10 to the power 23, which is a huge number. But important thing is we are dealing with a discrete system here. If it is a continuous system, this particular model of small oscillation, I mean small oscillation is actually an interface between a small system which is purely classical in nature, and there is a large system which can be treated as a continuous medium. Okay. So, in between we have a phenomena, we have a domain in which the masses are distinct. Each point masses can be identified individually, but their number is large as in large, it could be anything between 3 to 100, 200. Okay. But of course, for our purpose we will be dealing with systems with degrees of freedom of 2, 3 or 4, because we have to do the calculation on pen and paper. But in principle we will be developing a formalism which can be applicable for any n number. Anyway, so let us come back to this. What is important is V is a function of q1, q2 up to qn. Now, if q is equal to 0, that means if each of the mass points are staying in their potential, I mean in their equilibrium position, then we have potential of V where all the q's are 0. So, it can be written as V 0 0 0, right. Now, one way of dealing with small mathematically is if we take a Taylor series expansion of a function, okay, around for a particular parameter, and if I can approximate this, okay, let us do it. If I have a function of let us say V single parameter half k q square. So, what I can do is I can do a Taylor series expansion, or rather I would say any function, I do not know if it is k q square or so. I have a function V of q. So, what I can do is I can do a Taylor series expansion around q equal to 0. So, it will be 0 plus del V or dV in this case, dV dq at q equal to 0 times q plus half d2v dq square q equal to 0 q square, so on and so forth. Okay. So, the concept is here we try to see we try to compare each of this term with the first term V 0 and also with the initial value V. Okay. So, we have the metric or the measure of smallness is how small this full term is compared to your initial 0th order term, right. So, this is the metric what we follow, and typically what happens is, even if we take the quantity q to be very small, even if these derivatives are not very small by itself, the value of first derivative evaluated at q equal to 0, value of second derivative evaluated at q equal to 0, they are individually not very small. But if q I have taken a number which is really small, then q square becomes smaller than q, q to the power q cubed will be even smaller than q square, so on and so forth. So, the each weight of each term becomes diminishingly small. So, it is typically what we can do is we can keep maybe up to first order term, or sometime we keep up to second order term. Now, we can do the same procedure here, and we try to derive a Taylor series expansion of the function V around the equilibrium position. Okay. So, in this Taylor series expansion, this will be the first term, second term will be del V del q I at q I equal to 0 multiplied by q I. This is a summation term For each of these individual q's, we have to have a partial derivative, right. And then the second term del 2v del qi square evaluated at q equal to 0, and we have qi. So, actually that is a mistake actually. We should not write partial derivatives in like this in summation convention. What we should write is qi qj evaluated at qi j equal to 0, qi dot or sorry qi qj, and there will be a factor of 2 coming here, right. Okay. Now, if it is a potential function, and please remember that for a spring system where we have taken an example here, it could be any system actually, but the special in this special example q equal to 0 is a stable equilibrium position. That means, if I deviate any of the point masses or all of the point masses slightly from this equilibrium position, they will each of it will gain a restoring force and will try to come back towards the equilibrium. Okay. So, if this is the case, it is not if it is a stable equilibrium, and for stable equilibrium we have already seen that this, if this is your v, this is your q, this has to be a point, minimum point, not a maximum point. A maximum point is an unstable equilibrium, minimum. So, for stable equilibrium it has to be here. In principle, we can also have a metastable equilibrium which has a local minima at this particular point, and if I keep it small, small as in it will not it is so small that the restoring force is always towards the equilibrium position. Even that is a valid description. So, that is a valid definition of smallness, for which we can the amount for which we can deviate from a metastable equilibrium and gain a restoring force which will bring it back to the equilibrium. Okay. So, whatever it is, if it is either a stable equilibrium or a metastable equilibrium, both cases it is a minima, could be a global minima, could be a local minima. Okay. But if it is a minima, that means this term is uniformly going to 0, because we know that the first derivative at a minima for any function vanish, right. And it is a multidimensional function. I am just drawing a one dimensional version of the same function, but it is a multidimensional function of many q's. Okay. So, it will have a very complicated we cannot even draw it in the 2D plane, but what we can think of, like we did draw the configuration space, we can also try to draw the energy landscape where all the qi's will be along the x axis and the overall energy v, potential energy v will be along the y axis. So, in this complicated hyperspace, this will also have some kind of a minima, either local or global. Fine. So, in both cases, the del vi or del v del qi term evaluated at this particular point, if I am taking this as my x equal to 0, forget about this. Okay. This axis, this is arbitrary. So, we can take it here. Okay. So, this is my x, or rather q equal to 0, all the q's are 0 here, right. So, this is my position of local or global minima, and del v del qi is equal to 0. Now, another property is the second derivative at a minima is always greater than 0, right. That is something we have learned in during our school life itself, when we learned the how to find maxima and minima using derivatives. We have seen that the second derivative is always positive at a minima. So, this term is 0 unanimously, because we are okay. And let us assume that this smallness, we have to again define the small part. Smallness is such that the magnitude of this term itself is very small compared to this term. So, if this is the case, we can truncate it here only. We do not have to take the third derivative and above. Okay. So, of course, there will be more terms which is of the order of q cubed, we are just ignoring them. Now, this is 0 and this term, the coefficient of q I q j is positive definite. Okay. And this one is a constant term, and we know that if it is totally our choice whether we take the 0 of 0 of energy here or here. That is totally in our hand. If I can set this one as my ground level, I can set this one as my ground level, or I can say okay, this is my ground level. 0 is in our hand. So, what we can do is we can set this term equal to 0, and this is this is 0 by choice, this is 0 by definition, and the coefficient of this term which is a second derivative evaluated at a local or global minima is greater than 0. So, this potential function, although we took an example of a spring mass system where we know that the potential function has the form half k x square, but forget about it. If we have any potential function of any arbitrary shape like this, like this, or like this, or even asymmetric, like this, if I evaluate it around this minimum point and if I approximate it for small oscillation, small as in small such that we are not deviating much from the equilibrium, this condition is satisfied. The condition is this quantity, whatever it is, has to be much greater than this quantity, but again we are setting this to 0. Don't mix up this two. We are setting it to 0 just to shift the overall level. Okay. So, if this is the condition, each of this expansion, each of this potential when expanded in a small interval around the equilibrium will give you a quantity which is approximately equal to half k, or rather b I j q I q j, where b I j is equal to half del 2 v del q I q j del q j q I q j evaluated at q equal to 0 is greater than 0. Okay. So, this is your definition. So, essentially what we are left with only this term, and this we can just write b I j. So, v under the approximation of small oscillation v q 1 q 2 q n is approximately equal to this, and we can neglect the higher order terms. Right. b I j is this, once again it is a tensorial quantity, okay, because this is a depending on the values of I and j, the value will change. So, we can represent b I j in a matrix form. So, we have let us say I values going in this direction and j values going in that direction. So, I equal to 1, 2 up to n, j equal to 1, 2 up to n. So, each of this element it will be b 1 1, b 1 2, b 1 n, similarly b 2 1, b 2 2, b 2 n, b n 1, b n 2, b n n. Okay. So, it is a square matrix, positive definite, each of the element has to satisfy this criteria. Okay. So, it is a positive definite and must be real, because a potential function it is a real quantity. I mean, potential is a real function. The Taylor series expansion of a real function cannot be imaginary. Okay. So, we have a matrix which is real, symmetric and positive definite. Why symmetric? Because you interchange in the definition, you interchange I and j, nothing is changing. So, b 1 2 has to be equal to b 2 1. So, in principle if I just write one corner of the or one upper triangle of the matrix or this part and put zeros here, or should not put 0 actually, just describe only half of the elements. So, it is a n by n matrix. So, if I have n by information about upper n by n divided by 2 number of elements, I get the total description of the matrix. We have seen this type of matrices, real, symmetric and positive definite. Not okay, positive definite is something new, but your moment of inertia tensor was also real and symmetric, right. So, we have this. Now, in similar manner, if I try to describe the kinetic energy of each system, T, total kinetic energy of the system, will be a sum over I, okay, or rather it will be, it's just a minute, it's there is a form here, right, sum over I half m I v I square, right. So, where v I is the velocity of each individual system, you can also write it as q I dot square. Now, if I do that, it will be very long. Why? I put it like this once again, I show you. Because just please remember, when we wrote this, v I was the velocity derived in Cartesian coordinate system. Okay. So, v I is r I dot is equal to v I, right. Now, r I v I equal to r I dot. Now, what is r I dot? If you recall, r I dot was dr dt, which will be given by sum over k del r I del or del, rather write it x I, it will be matching with your previous notes, del x I del q k dot plus del x I del t, isn't it? This was the definition of velocity and in terms of generalized coordinate. Please remember, t was originally defined in terms of v i's, okay, and in principle which is given in Cartesian coordinates. In principle, we have to bring it in terms of generalized coordinates. So, in order to do that, what we have to do is we have to write this as half sum over I m I sum over k del x I del q k dot plus del x I del t whole square. Okay. So, if I open the brackets, please understand that I am talking about a general system. So, I have to do a general construction. Now, if I open the brackets, it will give you half, I will just write the final form of it, because otherwise it will take little longer. I mean, it is a very simple straightforward calculation. q k dot plus sum over k j k m j k q j dot q k dot. Okay. Now, what is T 0? T 0 is given by, okay, I will just open the bracket and you will get all these terms. T 0 is given by sum over I m I del r I or del x I del t whole square, okay, whereas m k is given by half sum over I, or sorry, no half here, sum over I m I del r or del x I del t del x I del q k, okay, and m j k is sum over I half m I del x I del q k del x I del q j, right. So, these are the three terms which will be coming in the kinetic energy expression. Now, out of this, if we are talking about scleronomic systems where constraint condition is not changing as a function of temperature, function of time, both these terms will vanish. This term, so if we are dealing with a scleronomic system, then del r or del x I del t is equal to 0 for all I. Now, if this is the case, then immediately we see that this term and this term will give you 0, leaving behind only the last term. Okay. So, you can see that this is also a tensor, okay, and the last term, that means only this term will survive, which is quadratic in generalized velocities and with a coefficient m j k, which has this particular tensorial form. Okay. And this is also once again, if you look carefully, so your total kinetic energy T will be equal to this. Okay. So, I am just getting rid of all this. So, going by the construction, okay, we do not even need j k, we have T equal to this. Now, this is a tensorial quantity which is also a function of coordinates q k and q j. Now, this will be the surviving term, which once again can be expanded. So, m j k, sorry, not a good way of writing. Okay. So, m capital M j k, which is a function of q 1, q 2 up to q n, can also be expanded in a Taylor series. So, the first term will be m j k evaluated at 0, then second term will be del so del m j k del q I plus 1 by 2 factorial del 2 del q k or q l del q m q l q m, like that. But this quantity is, now we are discussing a case of small oscillation once again. Now, if the displacement is small, we can safely assume that the velocities will also be small. Now, if the velocities are small, we already have a quadratic term in velocity which will be even smaller. So, if I now multiply another factor which is dependent on q I, so it will go as, you know, it is, I mean, it is very vague, but it is smallness squared, small into small. So, if I add a small another multiply it with another term which is again small, so it will be cubed, going as something cubed of some very small number, cube root, sorry, not root, but cube of some small number, and this will be even higher, quadratic in some small number. So, only in this entire expansion, only the first term for a real small oscillation, only the first term will survive, the other terms will be really vanishing. So, we can approximate this with simple m j k or rather what we can do is only this term will survive in the series, okay, and we can write this term as a j k. Okay. So, T you will be simply given as A j k multiplied by q j dot q k dot. Okay. So, A j k is the first order approximation of this particular tensor. Now, it sounds very complicated, but finally, we will be writing it only in terms of generalized coordinates. So, whatever coefficient the velocity factors will have will come into your A j k. So, you do not have to worry about all this mathematics, but I always thought that it is necessary for me to show you that simply writing in terms of, I mean, if we start by writing in terms of generalized velocities, it might not be the correct description. We have to do this transformation, we have to get rid of the first two terms of the transformation, third term will remain, even the third term will have a tensorial coefficient, which has to be expanded in a Taylor series to get you the correct mathematical expression. In reality, when we will be we have to find out, the kinetic energy and potential energy matrix elements. There it is very easy, because we will be looking at the expression and picking out the terms. Okay. So, that is something which is relatively easy. But once again, A I j also has this following properties. It is a real matrix, real because kinetic energy has to be a real quantity. It has to be a positive definite quantity, because if there is any motion and there is any energy, energy cannot go negative. Kinetic energy cannot go negative. Potential energy can potentially go negative, because you can have a maxima, but kinetic energy, whether it is there or the lowest value of a kinetic energy could be 0. And symmetric, because if you once again if you interchange j and k in this expression or in this expression, nothing changes. So, it is a real, symmetric and positive definite. So, we have for small oscillation, if I have a system which is scleronomic in nature, that is one condition we have to follow. So, it all boils down to this. We have a system which is scleronomic in nature around a stable equilibrium and deviated only slightly from the equilibrium, and we have T given by A I j q I dot q j dot. I wrote q j j k, but it does not matter, because these are dummy indices. We can change them, we are free to change them, and this is given by B I j q I q j. So, the Lagrangian of a coupled oscillatory system which is oscillating around its stable equilibrium position, and where the constant condition is not a function of time, that is very important. Your T or L can be written as A I j q I dot q j dot minus B I j q I q j. Very good. So, this is your general form of Lagrangian, and from here we can derive the differential equation, right? We can do that. So, please remember that form is once again for the parameter for the coordinate q k minus del L del q k. Very good. And once we do that, it will give you equation which will have A I j q, it will be q j. So, I have to choose the kth coordinate. So, it will be q I double dot minus B I j q I equal to 0. Very good. So, we have in principle solved the problem, because we have all this, we have the equation of motion for the each of these coordinates, and we are good. But look at it very carefully. This is a system of coupled oscillation. There is summation involved in this expression. There is a summation over both I and j running. Here also there is a summation over I running. There is a summation over I running into this system. So, that means it is not a single equation, but a system of, but it is a very long coupled equation. So, what we have ended up with, if we try to basically find out the individual equations of motion for each of the coordinate, we will get an equation of motion which includes all other coordinates. Each of the mass point with coordinate qm or qj, we get an equation which includes all the coordinates, right. So, that means if a system size is anything more than 3 or 4, let us say, it is almost impossible to solve this by hand. So, we need to have some other technique, other method in order to solve this coupled system of differential equations, which we will take up in the next lecture. Thank you.